Hey everybody, how you doing? We are going to start the next chapter, which is going to be all about acids and bases. But before we dig too much and like even begin to say like, oh, this is an acid and this is a base, first thing we got to do is look at water, because acids and bases are aqueous solutions, and it's because of water, believe it or not. And we also need to look at some of the characteristics of acidic solutions and basic solutions, because defining an acid and a base isn't quite cut and dry, black and white. It's not as easy as like yes, no, because why would nature be anything other than weird and complicated? So, before we get too far, what I want to start looking at is this. This right here. This is what's happening inside every sample of water, right? So this is also like this is the fundamental idea here with acids and bases. Is if you had two water molecules in a container, they're just bouncing around. Remember the whole kinetic molecular theory? Well, it's pretty simple to think that like if you have a mole of water, or like 6.02 with like, I don't know, 100 zeros behind it, there's a lot of water molecules, and you're bound to have some kind of collision where it's like the proper like energy and spatial orientation where you can break stuff apart, and that is exactly what's happening inside every sample of water. What happens is two water molecules collide, right? And what happens is like part of the one water molecule breaks, like a little hydrogen, like let's say this one. This hydrogen here breaks off and embeds itself inside one of these like electron clouds. And what we end up with as a result is this ion, which is called the hydronium ion, and this ion, which is called the hydroxide ion. Now, it just so happens that every single thing about acid comes from this ion right here. And every single thing that comes from basic solutions come from this ion, and they're both there in water. But the thing is if you have pure water, right, you can see that they're like for every one of this ion, which is a hydronium, there is one of these ones, which is called a hydroxide ion, right? So it's a 1-to-1 ratio. So as much acid ions that are there are an equal number of base ions. So pure water is neither an acid nor a base. It's like what we call neutral, because for every hydronium there's a hydroxide, and they can cancel each other out. Because if you're looking real close, you're seeing this right here, right? It is a system at equilibrium. So as fast as this happens, it unhappens. You know what I mean? And if you think about it, if this guy here has like, where'd he go? If this guy here has a positive charge and that has a negative charge, they're gonna snap back together and form those two water molecules again. It happens a lot. But what's really weird, at least I think it's really weird, is that no matter what, the concentration, these things right here, these brackets mean concentration. And we just talked about concentration. So the brackets mean concentration. So the concentration of the hydronium ions are exactly equal to the concentration of the hydroxide ions, right? They have to be. Why? Because of this equation right here. And now, the other part that's weird is that no matter what we do, heat it up, cool it down, the concentration ends up being this. All right, so take water. It's under like perfect conditions. It's nice and pretty and pure and everything that's wonderful. It's high quality H2O. You will have 1 times 10 to the minus 7 hydroniums, 1 times 10 to the minus 7 hydroxide. So this will be 1 times 10 to the minus 7, and this one will be 1 times 10 to the minus 7. And that's what it is in nice, clean, pure water. Got it? Got it. Oh, wait. Do you guys remember what the pH of pure water is? I don't know if you guys know much about the pH scale, but it's how we measure how acidic or basic a solution is. And something that is perfectly neutral is, 7. Get it? I hope you get it, because, well, if not, it doesn't matter, because you're going to get it soon enough, because we're going to talk all about it. So, like I said, oh, wait, before I go on. So this process here, This is happening in water all the time, no matter what. And that is important to know because it is a system at equilibrium. And that system at equilibrium can be tweaked. You know what I mean? So we can add things to water that will actually increase the concentration of the hydronium or the concentration of the hydroxide. You understand what I'm saying? I hope so, because here we go. Oh yeah, so we're not going to talk about what is an acid or a base first. What we're going to do is talk about acidic solutions and basic solutions. So then we can take a step back and say, okay, here's this substance. I put it in water. This is what happens. And that's how we're going to know whether it's an acid or a base. Because you can't always tell just by looking at the chemical formula if it's going to be an acid or a base. You have to look at how this particular compound interacts with water. You dig what I'm saying? Why does that matter? Because look, man, this is where the acid and the base come from. So if we throw something into water which increases the hydronium concentration, maybe, and then it's going to decrease the hydroxide, and it's going to make it like way more acidic. Same thing, opposite direction. If we take something that really increases the hydroxide ion concentration and decreases the hydronium concentration, then we'll have something that is a base. So let's look at what an acidic solution and what a basic solution is first, and then we will move on to greater things. So first thing, an acidic solution has more hydrogen or hydronium ions than hydroxide. And look at what I did here. This is the same thing as H3O. The hydrogen ion and the hydronium ion are interchangeable. So this H+, that is the ion that's actually doing the work. That's like the ion that makes it like acidic. However, it actually exists as an H3O, because if you remember, we started out with the regular old water, right? And that sort of rogue H+ embedded itself into one of these like unpaired electrons, and so the hydronium ends up looking like this. This is what it looks like, right? So these are the like two versions of the same thing. This is like the short version, this is like the long version. Hydronium is the long version, hydrogen ions are the short version. Got it? Excellent. But that's what makes an acidic solution. If you have like a big vat of acid, what it is an aqueous solution that has more hydronium than hydroxide. That's it. That's all you need to know about what makes an acidic solution a solution. And look, number 2, I just talked about that. So I'm just going to be like, bam, look at that. Also, if you're not sure what acids are or aren't, I want you to turn to Table K in your reference chart. Because Table K, right there, lists all of the acids and bases that you should be aware of. And right there, all of your bases. But that's Table L, that's next. But one thing I want you to see on Table K, if I go down Table K, the first thing that I'm going to see here is HCl. Right? Are you seeing that too? Like there, you can see it's making the hydrogen ion. Pretty simple. There's this one, H2SO3. So that one, pretty easy. There's your hydrogen ion. This is an odd one. That's an acid, but I don't see a hydrogen in there. Oh, technically CO2AQ. Because remember, you have to look at how the stuff interacts with water. Okay, so you can't tell just by looking at the compound always that something is going to make an acidic solution or not. But there it is on Table K, in case you're not sure which ones there are and which ones aren't. The next one is a basic solution. So same thing as the acid, only completely opposite, is it's going to have more hydroxide ions. Right? That's what makes it basic. And if you look at your table L, you'll see things like this. You'll see NaOH. Oh my goodness. There it is. Your hydroxide. What's next? Oh, the next one, that's super easy. KOH. My goodness, how can you not see that there's your polyatomic ion? There's your right, the hydroxide is like right there. Let's keep going down the list. And then I see this thing. That there's no hydroxide in there at all. Like at all. But just like I said, you got to look at how it interacts with water, not just the compound itself. So if we dissolve ammonia in water, it actually forms a basic solution. It increases the concentration of hydroxide ions. And that's all we got to know. That's it. It increases the concentration of hydroxide ions. So it's a base. You dig? All right, so an acidic solution has more hydronium ions. A basic solution has more hydroxide ions. Seems pretty simple so far. Oh yeah, what is a salt? So a salt, it's basically the leftovers of an acid-base reaction, right? That's the way I like to think of it. Like this, which you have right there, that's a wonderful academic definition, but really functionally, like when I look at a chemical equation, I'm like looking at stuff, I'm not thinking, is that anion from an acid and the cation from a base? Let me think of, dude, if you take an acid and a base and you react them, it's basically the salt is like what's left over after an acid and a base like cancel each other out. That's it. That is the definition of a salt. Not like a salt, but like, a chemistry assault. So here's what happens. If you take an acid and a base and you put them together and you you mix them up and react them, you will make two things. The first thing that you're going to make is salt, and that's what we're going to look at in just a second. The other thing that you make is water. Always, because here's how it works. From the acid, we get the H, right? The hydrogen ion. And from the base, we get the OH. And any time a hydrogen ion can come near a hydroxide ion, they are going to make one of the most stable compounds in the entire universe, right? So these things are going to make the water. Why? Because it is the most stable thing there is. Nature loves water. So what's left over? Well, what I like to do is I'll scribble out the H and the OH so I don't have to worry about using my eyes because, they don't work. So the positive thing is my sodium, the negative thing is the chlorine, and they get together because they're just like in the beaker, create what's left over, a salt. And in this case, it's table salt. That's how it works. The hydrogen and the hydroxide cancel each other out and make water. They disappear. They turn into this the solvent. The leftovers that are still floating around inside the water, that is your salt. And so if you want to extract the salt, you just boil off the water, and there you go. You've got a beaker full of salt. You got it? So an acid and a base makes water and salt. You should say that again, because an acid and a base makes water and salt. I think that's like Dr. Seuss month or something. And I'm telling you, I think I'm spitting fire here. Because an acid and a base makes water and salt. An acid and a base makes... I think I just need a beat, and I've got I'm gonna go on tour or something, because that would be great. So look, here's what we're gonna do next. We are going to look at the characteristics of an acid and a base. So of an acid and a base solution, really. So characteristics of acids and bases solutions. So we looked at what is an acidic solution, what is a basic solution. An acidic solution has a lot of hydrogens, or more hydrogens. A base has more hydroxides. And so what is the result? What happens? Well, in an acid, all of the characteristics come from H3O, from the hydronium ion. And for bases, they all come from hydroxide. Always. All right, so that's just how it works. As far as tasting, yeah, man, acids taste sour, and humans have learned to love the taste of acids. That's why we have like vinegar-based salad dressing. That's why we like citrus fruits, because vitamin C is actually like a really, really weak acid. There's so many things that we like that are like acidic, like Sour Patch Kids. So good, so good. On the other hand, bases, these are bitter. Bitter like we have a natural gag reflex. It's awful. Like if you tasted anything basic, the first thing you're gonna do is you're gonna retch and want to spit it out. Yeah, that's the best. I don't have any good examples for what bitter tastes like, because one of the problems with basic solutions, and this ion right here, is that it really likes breaking apart polypeptide bonds, which is what holds the proteins that make us together. And so I'm not really into eating those things which is why we have evolved to not really like things that are terribly bitter, because usually, often, it is a signal that the substance is a base and is going to be really bad for us. So who knew that like sour tasting things are acidic, and we have evolved to really enjoy sour things because we need, nutritionally, we need lots of these like acidic things, but we have evolved to hate bitter things because it will actually cause damage. Yeah. Also, a weird thing, bases will often feel very slippery. So what you can do for this is if you if you put a little bit of bleach on your finger, right? It feels very slippery. Like you try to rinse it off, and it feels really slippery. Whereas acids, I don't know if you've picked up on this, it just feels like a liquid. You know, it just feels like water. There's really no, you can't really tell just by splashing around. If you close your eyes and splash around in an acid and then splash your hand around in some water, you aren't going to tell the difference at all. Nothing. However, a base, you will feel very slippery. And here's the fun reason why. So our bodies are made out of skin and water and all kinds of stuff. So I guess our bodies aren't made out of skin, but the outside of our body is skin, which is primarily water, right? And bases are basic because they have lots of hydroxide. And if you look at this hydroxide, it is basically half of a water molecule. And our skin has been made to absorb moisture so we can stay nice and bendy and move around without cracking, right? So the problem with that is that that hydroxide ion is absorbed very quickly and easy into our skin, right? And like I said before, with like the whole tasting bitter and like really gross, is that it breaks down polypeptide bonds, which hold our molecules together. So when we touch a base, like something like bleach, and we get it on our fingers, what happens is those hydroxide ions absorb into our skin very quickly, and they undergo a chemical reaction, which makes the molecules of our skin into a soap-like molecule. So that slipperiness is basically our skin turning into a soap-like molecule, and that's why it's slippery, because soap is also kind of slippery. And it takes a long time to rinse like bleach off of your hands because it has literally soaked into your skin. So you got to rinse until, you know, all your skin soap molecules are gone. That's gross. Maybe don't do that. Or do, I don't care, but don't play with too much bleach because you will hurt yourself for reasons I have just explained. Next! Both acids and bases conduct electricity. What? Yeah, they conduct electricity because, by definition, an acid has to have hydrogen ions. Bases have to have hydroxide ions. And to conduct electricity in water, you must have ions. The electricity kind of uses the ions to kind of hopscotch through the water. So there you go. They both conduct electricity. And they do that because acids and bases are these wonderful things. They are electrolytes. I know we've talked about this before, but now you gotta know it. So what is an electrolyte? Because all of the good sports drinks have them, right? Well, an electrolyte is any compound that conducts electricity when you dissolve it in water. In other words, it makes ions in solution. You dig? Doug, that's what an electrolyte is. Just so happens that the sports drinks are like saying, oh, they've got such great ions and stuff. They're giving you sodium and potassium, right? However, fun fact, remember acids and bases, they're supposed to conduct electricity. And an electrolyte is something that's supposed to conduct electricity when you dissolve in water. Dude, if you go and take almost any sports drink like your Powerade, your Gatorade or whatnot and do a conductivity measure, it almost doesn't conduct electricity because it has such a low dose of electrolytes. There's almost none in there. They sprinkle it in there so they can be like, oh yeah, lots of electrolytes. It's mostly just sugar and food coloring and flavor. But I don't care. I still drink them because they're like delicious. They're delicious. So here's the thing. We can also tell if an acid or a base is strong or weak based on how well it conducts electricity. Now, strong acids or bases are going to conduct electricity very well because they dissociate. They break apart completely and they never get back together. So when you put these substances into water, they dissolve and they're gone. It's like you'll see this in the chemical reaction. Straight arrow, nothing coming back. However, weak acids and bases, right? If it is a weak acid and base, it's because they conduct, it's because like when they break apart, they can get back together again. And they do something like this, right? It's actually reversible. So they can break apart and form ions, but they can actually snap back together. That makes sense? And I want you to notice, I want you to see, do you see here or here anything? Do you see anything at all about the concentration? No, you do not. Because the definition of strong and weak has nothing to do with concentration. That would be a concentrated acid or a concentrated base. Being a strong or weak acid or base has only to do with how well they break apart in solution. Locked and loaded? Lovely. Let's move on. This is the next one. Acids react with bases to form water and salt. Bases react with acids to form water and salt. Look at that. I think we just talked about that. But now we've got a new word because it seems to be sort of important, and that's called neutralization. This is when an acid and a base react to make water and salt. There's no more acid. There's no more base. It's gone. That's why they say neutral. It's been neutralized. All gone. No acid, no base. Taken away. Bye-bye. So long. Nothing but salty water left over. So you can take a beaker full of hydrochloric acid that if you poured it on your face would dissolve your eyes out of your skull. You can take a beaker of a base that is so strong that you wouldn't be able to finish swallowing it before you, like if you tried to chug it, because it would dissolve most of the inside of your oral cavity. You pour the two things together and you can have table salt. It's weird, but so is nature. So neutralization is when an acid and a base cancel each other out, making water and salt. Got it? Just like this, right? So this is our base. How do we know? This is our base because of our hydroxide ion, and I'm pretty certain this is going to be my acid because it's got the H. You understand? So the H and the OH get together to make water, and then the thing that is left over, like whatever the two things that are left over, make the salt. And if you notice, sodium is on the left here. It's on the left here because it's going to be it's in the positive side. And chlorine is on the right here and it's on the right here because it's on the negative. You get what I'm saying? Lovely. All right. So for this one, which one is this? Is this an acid or a base? Well, I see hydroxide. This will be my base. Right? And it's pretty easy to see that this one is going to be my acid. You dig? And then this one, that must be my salt. And if you don't know what that is, you're just being silly. All right, let's do this next one. So acid and a base makes what and what? So I know if it's an acid and a base, the first thing I'm going to make is water. And the next thing I'm going to make is some kind of salt. So the way I try to figure out what salt it is, I'm going to get rid of my H. I'm going to get rid of the OH. And what am I left with? The positive is a potassium. And the negative is a chloride. Potassium is +1, chlorine is -1. If I do my crossover method, it's a 1-to-1 ratio. Bam. There it is. There's my neutralization reaction. Lovely. That was awesome. That was easy. Let's see about this one. And again, it's going to be the same thing, just like a little bit different, right? Acid and a base. See, there's my acid. And then here's my base. Acid and a base makes water. And let's see what the salt's going to be. So I'm going to ignore that. There's my PO4 and okay, calcium. So calcium is my positive thing. And if I look at the periodic table, it's got a charge of +2. And here's my PO4. It's my polyatomic ion. Now I could either look in the reference table to see what the charge is, or I can see that here it's bonded to 3 hydrogens, so the PO4 has to be a -3 to cancel out the 3 pluses from the 3 hydrogens. Okay? So now we're going to do the crossover method over here. 3 is going to be dropped down to the calcium, and the 2 I'm going to give to my PO4. But don't forget, if it's a polyatomic ion, we got to put that puppy into brackets. All right. I feel like I'm almost done. I'm just missing one little thing. Balancing, your favorite. So here's the thing when we balance acid-base reactions. I've got hydrogens here and here, and I'm not that good. So I'm going to skip them because that looks difficult. hydrogens are always really hard, so I skip them. So I'm going to start out with my PO4s. I've got 1 here, 2 here, so I'll put a coefficient of 2. So I'm starting over. Remember, I put a coefficient over. 2 times 1 PO4, 2 PO4s, 2 PO4s, 1 calcium here. I've got 3 calciums over there, so I'll put a coefficient of 3, starting all over again. 2 PO4s, 2 PO4s, 3 calciums, 3 calciums. So here I've got 2 oxygens in each compound, but I have 3 compounds in all. So that's 6, right? So I'll have 6 oxygens here, right? So that's 2 oxygens. I'm going to distribute my 3, total of 6. Yep. Excuse me, 6 and 6. Okay, so finally, now that everything else is done, let's go double check my hydrogens. So 2 times 3 is, I've got 6 hydrogens here. 2 hydrogens times 2, that's 6. So 6 plus 6, I've got 12 hydrogens in all on my reactant side. 6 times 2 is 12. Man, I should do this for a living. Done. That wasn't so bad, now was it? Nah. So let's do this other thing about indicators. Everybody's seen indicators. They're the things that change color in an acidic solution or basic solutions, like the little strips we test pool water with and stuff. They just change color. Now what we need to know is that acids change indicators color. Bases change indicators to color. And there's this thing that they like to have in academia, and I don't know why. They like to know, they want you to know all about litmus. Probably because if you have an unknown thing, you take litmus, dip it in. If it turns it red, it's an acid. Dip it in. If it's blue, it's a base. So watch. This is how you're going to remember. Watch. You got to do like, ready? Base. You got to go like that. Base. Because bases turn litmus blue. Try it. Bases turn it blue. Go ahead. Try it. Bases turn it blue. How are you going to forget that? Bases turn it blue. Now, the other one, the acids, here's the thing. I wish I was clever enough to come up with this by myself, but I don't. It's Chloe. Much props and credit to Chloe. Because baboons have red acids. Turn litmus paper red. You thought I was going to say a bad word. Because baboons have red acids. Turn litmus paper red. It's hilarious. I love it. Yeah, you just got to remember that, guys. Litmus paper, baboons have red acids. Turn litmus paper red. And then bases, turn it blue. It is going to be a question I will ask of you, guaranteed. So let's move on. The last thing we need to know about acid and base solutions is that acids, most acids, will react with metals to form hydrogen on table J. So table J is a brand new one for us. We're going to have to get cozy with it because Lord knows we're going to need to be familiar with it for a lot. It's right here, table J, right? So look at all these metals. And right down there, there's hydrogen right there, okay? Any metal above hydrogen is going to react with an acid and form hydrogen gas, and this is kind of what it looks like. So zinc is definitely above hydrogen. If you put it into an acid, basically what happens is you have hydrogen ions and you have chloride ions. And these hydrogen ions they're so positive they just rip electrons off of the zinc metal and they turn into hydrogen gas. And then the zincs turn into ions. So the hydrogen ions have high enough electronegativity that they can tear an electron off of the metals, which typically have pretty gosh darn low electronegativities, if you recall periodic table chapter 2 and all that good stuff. So what else do we got? Nothing. We're done. And so to practice with this, we are going to look at water, the neutral substance, and acids and bases in water. We're going to look at what happens in pure water. We're going to look at what happens in acids and bases when you put them in water and all that kind of fun stuff. Gosh, man, we're going to have so much fun. This is going to be awesome. I'm going to have a great day. I hope you do too. And have fun with those things. Man, that looks like some good times right there.